Hello everyone. My name is Boyang Chen. I'm a database development engineer at the Douyin Group. The topic for my session today is multi-stream real-time data analysis solution with Apache Doris. So my presentation today will consist of 4 sections. First, in section 1, I will display the usage of Doris inside the Douyin Group. Second, I will introduce you multi-stream data analysis as a common use case with some current data analysis solution based on Doris. In section 2, I will talk about some of the challenges we met in reality while dealing with multi-stream data analysis based on Doris. And in section 3, I will demonstrate some of the solutions that we bring to address those challenges. And finally, in future works, I will share some of our future plan with Doris for our team. So now, without further ado, let's get started. So I would use 3 keywords to describe the Doris usage inside the Douyin Group. The first keyword is real-time data warehouse, as Doris could provide powerful ELT ability and efficient query performance. We've been building real-time data warehouse around the Doris. So they are mainly consist of 2 platforms. The first platform is the data integration platform, which provides X to Doris and Doris to X templates task, which controls the data imports and exports of Doris. The second platform is a data production platform, which provides scheduling for Doris to Doris task. And the second keyword is data serving, as Doris could provide high-QPS and low-latency data analysis. So we've been using Doris as a computing engine for multiple business lines like live streaming, e-commerce, and advertisement, and so on. And the final keyword is data lake, as Doris provides powerful data lake ability, so we've been using Doris on ES and Doris on Hive. In short, we've been using Doris extensively inside our group over multiple business lines, with more than 100 dedicated clusters and a total of more than 300,000 cores. So in our daily practice, we find for business scenarios like e-commerce, it's a common requirement to combine multiple source tables into one largely normalized tables. I will use a classic e-commerce example. Let's say a user makes an order online. So in the fulfillment of the order, it may have to go through several steps. First, the user may make the order on the online shopping mall department, and they may have the logistic department to deliver the product to the customer. And finally, the user may apply for after-sales service. So as the event tracking systems keeps reporting back the different parts of information of an order. So to get a full picture, to do data analysis, we have to put different parts of those information together. And there are mainly 2 challenges of this. The first challenge is that first, different streams comes with a large amount of data. And the second challenge is that the different part of the information may come in at a different point of time. So it's quite challenging to do data analysis in this situation. So there are 3 options that allow us to do multi-stream data analysis on Doris. The first option is that we choose to do multi-stream join with external systems, like some streaming process systems internally, and we join those different streams together. And in Doris, we only ingest the whole the whole record. But the problem behind this is first is that, as I said, the different parts of a record may come in at a different point of time, and the time period could be quite long in some instances. So it means that you have to store a lot of states to do such multi-string join, and it will consume a lot of computing resources. And the second problem is that as you added the extra process with external systems, so it will cost you more human resource to maintain these external systems and lower the overall maintainability. So the second option is that Doris offers a synchronous materialized view that it will allow you to create a synchronous materialized view across tables and to refresh the materialized view while the table updates. But the problem behind that is that in Doris, we split the table logically with partitions, and the minimal refresh unit of the synchronized material view is partition. So it means that basically means that if you only update a few records in one table, and for the refreshment of the materialized view, it will recompute the entire partition, so that you are wasting a lot of computation power here. So our goal here is to maximizing the query performance and visibility of changes. So finally, the most promising option seems to be to do upserts or partial update with Doris. So in Doris, there are three kinds of data models. The first one is duplicate model, which only append data only. And the second data model is aggregate model. It will allow you to aggregate records by some Python aggregate keys. And the third model is unique key model. You could think it like some special kind of aggregate model that either restrict the aggregation method with replace only. So to do partial updates, it means that we only changes a fraction of one record with some like the picture suggests, like the picture suggests that for string 1 we may want to update the 2 columns here, and for string 2 we update the 2 columns here, and so on, so that we aggregate those changes with aggregate key. So in Doris, we call the parts of columns we would update as the value columns, and the columns in the aggregate key as key columns. So there are for upserts, there are mainly two methods that we can do, allow us to only update a fraction of the record. For the method 1 is aggregate model with replaces not none as the aggregate function. It basically means that you set the aggregate key as set the key columns as an aggregate key, and set other columns you want to update, and set the aggregation function as replace if not none, so that when you do inserts of parts of the string, you will insert key columns and the rest and the values of the columns you want to update, and leave the other columns as none, so that you could change the fraction of your record. But there are two problems behind this. Is that first, it's aggregate key model, so you are forced to do merge and read while you query. And the second problem is that since it's aggregate model, so some of the storage layer optimization that opt for unique key model cannot be applied. So you get slow query performance for this method. And the second problem is that replacement order uncertainty. The as we all know that the data shuffles all around in the data production line, so it's always hard to to ensure a particular order of your data in your data production line, and so sometimes you may get your newer data be replaced by your older data, so that's a problem here. So another method that comes with Doris more than version 2.0 is that the unique key model have enabled merge and write, and it also supports partial update. So as I take this example from the Doris official website. So once you enable the partial update ability, so you could change a partial column of that unique key model. Just as the example says, you could update the order status from pending to be shipped. So since it's a unique key model, so you get good query performance. And for unique key model, the Doris also offers sequence column feature for you to control the replacement of your updates. But there are still some challenges remains. So the first challenge still comes with the replacement order. Although the Doris have provided a sequence column for the unique key model, as you can see here that the key mechanism of sequence column is actually by adding a hidden column in the storage layer. So the user could specify the sequence column as either one of your columns, or you could only specify the type and specify the sequence column once you do insert. But the minimum update granularity of the sequence column is row, which means, like the example says, you have to update the entire row once you do updates. So once the Doris finds that if the sequence column in this case is a modified time, which if your records have modified time newer than the current record in the storage layer, it will replace it. But in our stream of multi-stream data analysis, it's also important to preserve the sequence of replacements of each data stream, which each data stream is part of the entire record, which means some partial columns, not the entire record. So the sequence column is not able to achieve that. So that's challenge one. So for the second challenge is that for TTL, that for Doris, data lifecycle management relies on dynamic partitioning with key columns. So Doris can automatically manage that lifecycle management with range partitioning, as user could set the partition config in the data in the table properties, but sometimes it's impossible to do so. As if you want to do dynamic partitioning, you have to set a unified key column as a partition column by its values. But for some of our cases, that is hard. For, as I said, the different data stream of one record may come in at a different point of time. So sometimes you may not be able to find such a column to be served as the key column. So like this example says, no, there is just no proper candidate of partition column in these cases. So you might think, if we could just do scheduled deletion or periodical deletion with that, well, for the first, that is, as the note suggests from the Doris official website, that deletes just do not work on non-key column. That only conditions on the key column can be specified when using aggregate or unique model. Even if the delete is actually working, as we all know in big data systems, that there are mainly two ways of deletion in the append-only systems. Like for the first one, is that you only insert a version of your delete condition in your data, so that the data only actually gets deleted once it's do compaction. And the second way of doing that is that you just insert your data you want to delete all over again, but setting the delete flag as true, and delete those data when you do compaction. Those two methods correspond to deletion and batch deletion in Doris, but either of those two methods, it will give you bad query performance and slow down your compaction, and its compaction is quite significant while you do real-time data analysis and data ingestion. So the second challenge is that, as I said, we've been using Doris in multiple business lines with a lot of dedicated clusters. So in some business lines that we currently have multiple independent clusters. So that each cluster is a data warehouse associated with different usage orientations. There are various multi-stream scenarios that demand data production based on different tables across different clusters. So there are currently several ways to deal with that. Is that we can store data with duplicates in different clusters, but that could cause you got data redundancy problem and you got data consistency problem. And another way of doing this is through JDBC catalog, as we know that Doris is MySQL compatible, but it will slow down the overall performance. And the Doris also provide with cross-cluster replication function feature, but that it will still have the data redundancy problem. So to address all the challenges I've mentioned about, that we have proposed 3 key features to address each one of those challenges, and I will introduce them one by one. So for the first challenge, for the first challenge of replacement order of different data streams, that we have implemented the sequence mapping function feature that it allows stable replacement order for each string determined by a sequence mapping column. As the example says here that we have 2 strings that we want to ingest into the example table. That's for string 1, we have A as the key columns and B, C as 1 as a value columns. And for string 2, we have A as a key columns also, and as D, E, S2 as value columns. So we can set in the properties that allow us to set in the sequence mapping column for string 1 as S1, which controls the B column and the C column, and the mapping sequence column S2, which controls D columns and E columns respectively. So, as example, you can see here that we effectively divided the record into different column groups with sequence mapping column, which allows us to control the replacing order of each string with its respectively sequence mapping columns. As string 1 can update A colon B colon C and S1 column with S1 column controls its replacement order, and for string 2 it has as column S2 controls the replacing order of A, D, E. Yeah, and that is for feature sequence mapping. And for the second problem of data life cycle management, that we also implemented row TTL. So the row TTL aims to get rid of your expired data in a more flexible way. And we have implemented it in the data storage layer, that we add a column just like sequence column. We add a hidden column of your TTL time. So the key mechanism behind that is that we actually do the data deletion while you do acyclic compaction in each of your replicas on each computation node. So there are a lot of key features of it. The first one is that it allows you to have a free selection of reference column, as you can set it either as the key column or value columns, which you can do, so it gives you a flexibility of doing data lifecycle management. And if even if you can do that just like the sequence column, you can choose no column at all, and you will automatically fill with PTO column with the date that your data ingestion. A second key feature is that it's also compatible with rollouts, as it just add in hidden column, so that it also can be added automatically to the rollup you built on the table. And the third key feature of that, since it's deleted comparison, so it just don't have extra computation waste while you do the query. And the final key feature is that since the comparison happens independently on all the replicas in different compute nodes, so you may get into that inconsistency while you come into some expired data. So we also added the default predicate to filter those expired data for while you do the query. And for the multi-string across clusters, as we also implemented the Doris external table inside of Doris that allows you to query data outside of the Doris, but you could get nearly as a native cluster of query performance. So there are a couple benefits of that it not only allows you to query results of other clusters, it also allows you to do cluster ELTs. Just like the example on the screen says, that you can do inserts from other clusters and insert the results from other cluster to the current cluster. And as you can do such ELTs, so that it also allows you to do workload isolation and optimization. And an example that's in some of our business lines that we have dedicated cluster for data production and a dedicated server for data serving. And for those clusters in the data serving, that we only consumes data from the data production clusters, so your data production will not affect your query. And for the final benefits is that you may have different figures that are computed across different clusters. So that Doris external table also allows you to do cross validation for data consistency. So here is a basic query execution with Doris external table. As you can see on the screen, is that in step 1, the user could create a catalog for foreign Doris cluster, and as user made a query request, so that the main part of it is just like a normal query, but with some RPC from local FE to foreign FE for information like table schema, partition info, and statics like row count of tables to do query optimization like join reorder, and the tablet info and replica info for your table, so that will generate the query plan based on that, and will execute the query plan just like any other queries. So basically, you just add 2 RPC from local FE to foreign FE. So in our daily practice, it will, for the same data centers, it will nearly cost like less than 50 milliseconds. And yeah, that's used for the Doris external table. Okay, and finally, for future works, there have been mainly four directions that we've been still working on. That will, for the first direction, that will continuously to optimize multi-stream data analysis scene. that for ROTTL, we have been implement it on relatively 1.2, so we are still adapting it, transplanting it to the most recent version of Doris, and we are looking forward to contribute it to the community. And for the second point is that we've noticed that the Doris community have recently proposed for flexible column updates. I will explain it like in the past, you have to specify the schema you want to alter before you do the insert. But for flexible column updates, is that it allows you to allow Doris to automatically do partial updates with JSON data. So we're looking forward to incorporating our data production. And as we noticed that Doris have introduced a compute storage couple mode in Doris 3.0, so we would also like to introduce us into our development, since it could provide elastic computing resources and reduce the storage cost. And for another aspect is that we'll continue to do real-time data warehouse construction with the platform itself, and adapt the Doris with some interfaces that will make it work even better with the platform. And for the final point is that for data lake, that we have noticed that Apache payment as an emerging lake format for a real-time lake architecture. So have been working on to how to incorporate that into our data production line. So that's all for my sharing today. So thank you all for listening.